I appreciate you guys for having me and being flexible with the change in plans. Last week was a little crazy in Houston, Texas, where I live. And thankfully, we did postpone because I did lose electricity when we were having the meeting again, which was an exciting week. I know it sounds like we're a bunch of weenies down here when it gets a little cold, but they don't put insulation in the walls down here. So I think they just wadded up newspaper and put it in our walls. And the freezing temperatures were a bit crazy. So I hope everybody can hear me well. And if I need to do anything different, please let me know. I'll try and have the chat room up so I can see that. I really wish that I could have done this meeting in person. I don't like to admit this, guys, but I did grow up in Tacoma, Washington. I normally like to say I grew up in Seattle. And I have a brother that lives down in the Portland area and in Malala, and then I have another nephew that lives in Woodburn. So next time I'll have to make the trip up and be able to see my parents that still live in Tacoma and go down and see my family in Portland as well. Well, I heard some very kind words and I appreciate you guys for having me. Hopefully I don't let you guys down today on the presentation. I have a talk on why heat input control is critical. And I'm going to try and go through this and talk about it from a perspective of some of the basic metallurgy so we understand sort of why it's critical. And working with Boyce, I picked 4 different alloys we're going to take a look at. So just a brief outline is we want to talk about A36, which I sort of look at as a good starting point because A36 is very easy to weld and it's very forgiving with our welding procedures and our processes. We're going to talk about A514, A517 type steels, T1. I hope that some of you all are using some of those steels. Also. That's a very nice alloy to talk about because it is it's so challenging to work with. And then we're going to talk a little bit about stainless steels, sort of something that can build on the carbon steels that we have. And then we're going to talk a little bit about aluminum alloys at the end, and particular, the effects that they have, both the heat treatable and then the strain hardening. I really appreciate any comments or questions throughout the talk. I have no problem in taking them. Just am having a hard time seeing the chat window pop up. So you guys might have to help me with that or unmute yourselves. We're going to talk about it from a basic metallurgy. I really want to get into talking about the chemistry of the different alloys, understand how these alloys are made, their mechanical and thermal history, because while they're inorganic, they don't have feelings like we do. They do have a history, and how the alloys were made and how they were manufactured does ultimately affect how we weld with them. And so it's important to understand sort of where they come from. We want to use that then. I want to build on the basic metallurgy to predict how welding will change the alloy. The heating and cooling rates, we're going to talk a little bit about time temperature transformation diagrams, the phase diagram, and then how some of those things affect the mechanical properties at the weld and the heat affected zone, how we can lower the strength, we can decrease the impact properties and or raise or lower the hardness values. And then I'm going to focus from that into the stainless steels and the aluminum alloys. So hopefully that works. And that's a nice picture that we have of, that was the space shuttle when it was still flying. But what I really liked about that is the large fuel container there, the orange looking one. In the early 2000s, they switched over that material from, I believe it was an aluminum copper magnesium type to an aluminum lithium magnesium. And just by changing to an aluminum lithium, the lithium lowered down the density. It increased the strength and lowered the density. I believe it lowered the overall weight of the space shuttle by about 2 tons. So they could bring up a lot more cargo in the sense of satellites. And so it's really interesting how we can play with these materials. And probably some of you out there are dealing with the aluminum, lithium, and a lot of the aluminum alloys there on the West Coast. So as we get into A36, I sort of did a preface, I'll hit it. I like A36 because it's a nice as-rolled steel. It's somewhat of the vanilla of steels, lower carbon and manganese. It's got a nice yield strength of 36 KSI and a tensile strength typically around 70, but 58 to 80. And really, it's kind of hard to mess up A36, but there's a few things that you have to look at when we're working with the A36. Namely alloys that are coming in maybe with higher chemistry than we anticipate, alloying elements that we wouldn't normally see, and that can affect when we take a look at the CMTR. If what we really have is just a low carbon manganese steel, or it's having some trace elements of chrome or nickel in it that could raise the hardenability. The A514, oftentimes we call it the T1 type steels. Those that we're going to talk about are all quenched and tempered. So a different manufacturing process in the sense that they are raised up, quenched, and then tempered to have a nice tempered martensite. They have a lot going on because if you look at the alloys, they have carbon and they have manganese. I use the grade F as an example, but they also have chromium at a healthy amount, around 0.5. I have a can't see my whole screen. That's why. Nickel, it has around a little less than 1% nickel. Molybdenum, which is a very high strengthening. It can really add to hardness. It also adds to strength. Copper for some corrosion resistance and some wear resistance. Vanadium, and it's what's interesting, I like to point out, I don't know how familiar you are, but the vanadium and boron, if you look, those look like really tiny numbers. Vanadium being about 0.05, compared to manganese at 0.6 to 1%, and the boron is even smaller. It's 3 zeros, 555 and 666, but the boron and vanadium are very small atomic elements, and they're really, really strong. They can add a lot of strength, and they also can give us a lot of problems from cracking and raising the hardness. So when we look at those numbers, even though they're really small, they're incredibly strong as far as alloying elements. So the 514, I have a tendency to call some of these steels the kitchen sink steels, and I call them the kitchen sink because it's sort of like everything that was in the kitchen sink fell into the melter to be able to make these steels. There's a lot of activity happening, as well as the heat treatment that is going through the quench and tempering. And of course, the yield strength is over 100 KSI, and then the tensile strength is 110 to 130. And all of the 514 and the 517 grades sort of fit within that range. Stainless, this is a little snippet of what I've got. Stainless is, as we move into that, it builds on some of the carbon steels. It's not stainless if it doesn't have chrome, so we have to have at least 12.5% chrome. And here's a chrome iron phase diagram. But we have ferritic stainless, austenitic stainlesses now have both chrome and they add nickel in, around at least 8% nickel. You have martensitic stainless that we'll see quite a bit in rolling mills and other sorts of high strength applications, the duplex and the precipitation strength. But they all have some of the similar basic needs in the sense that they have the chromium that imparts the corrosion resistance, the chromium nickel balance sort of for the 300 series or the austenitic. And then someone will add molybdenum. But carbon is where I really want to talk. And what's really important with most of these alloys is controlling carbon. And we have the L grades and the H grades. It's trying to make sure that the carbon is not moving around and tying up the chromium and then losing its corrosion resistance. So we'll get into a little bit of the intergranular growth and the corrosion, the sigma phases and so on. I had to put a DeLorean in there. I wish they would have had a really good engine in that, but they ended up with a Peugeot, Renault, Volvo. And if any of you guys come down to Houston and have, please come and visit me, obviously. But before you do that, if you fly into Bush Intercontinental, DeLorean Motor Company, a guy bought up all of the parts from Northern Ireland, and they have a place about 5 minutes away from the Bush Intercontinental Airport. And they still will fix up DeLoreans, and they're trying to build DeLoreans and even build an electric DeLorean because they have so many body panels and chassis still left. So that's just a little note about DeLorean. Stainless steel body, metallurgy. You got to throw a DeLorean in there. Aluminum alloys, not going to lie, guys, aluminum alloys are a little bit outside of my daily area of expertise. But aluminum alloys are very interesting and they can be very challenging. We have the typical alloy grades up here, and there's a really nice chapter in, I believe it's volume 4 of the AWS handbook on aluminum alloys. But aluminum alloys, we get into using them for lighter density. It can be more difficult to weld due to the higher thermal conductivity. They spread the heat out really fast. They have a really tight aluminum oxide. What's interesting with these is similar to sort of that T1, very different, but similar. They're relying on a lot of alloying, and they're also relying on their heat treatment or cold working that goes in. And so anytime you're putting in either mechanical, like cold working, or you're putting in heat treatment, as soon as we go to weld, it has a tendency of erasing that memory. I kind of use the memory loosely, but it erases the history of how that aluminum alloy got its strength. Got its strength either from doing mechanical deformation or going through heat treatment. So there's some really good documents that can go out that decipher or help us decipher the different type of conditions of the aluminum. A very common one that we'll see used a lot even outside of just welding, but just in structural materials, is the 6061 T6. The T6 down here talks about the solution heat treatment and artificial aging. We'll talk a little bit about precipitation, and I got to move it. I realize I only have an hour, so we'll keep it. What is metallurgy? I like to call that everybody on the line is a metallurgist, whether you are a welder or you're a welding engineer, or you're a design engineer, because a loose definition, everything we're doing is manipulating metals. We're taking metals, whether you're melting the metals and you're working at a steel foundry or a metal foundry, you're rolling the material. We're all metallurgists. And so it's very important that as we're welding, we have some basic understanding of what makes that metal different. And this over here, the picture is a materials tetrahedron, and I like it. It's a way of describing, each one of these corners describes sort of why you would pick a material. And the reason why I like it, just really brief, is you can make the best material that has the best performance, for example, ever. But if your decision is only focused on the material performance and you forget that you actually have to process the material or roll the material or weld the material or make something out of it, and you really can't do those things, then it's really not the best material for the application. Everything that we do has to balance the processing, another word for fabrication, the performance of how it's going to work, the properties that it has. So we're all metallurgists, and I think you guys remember, you'll see this periodic table of elements. Maybe you haven't seen it since high school, maybe you've seen it in college. For me, because I'm a little bit different, I have it hanging up on my whiteboard in my office because it's something that we use every day. What's nice about it is that every alloy and every material we have, from the carbon steels, the A36 is simple because we're just using the carbon, we're using some manganese. And the 514, the reason why I call it the kitchen sink, it's kind of like the periodic table of elements sort of fell down into the melter. Everything went in there, and it's relying on a lot of different alloying elements. And the more elements that are in a material, the more challenging it is. Materials we have, the carbon steels are going to be body-centered cubic. This is the arrangement of how the atoms typically arrange themselves. So for the carbon steels, they're going to be body-centered cubic. For the aluminum alloys, they're going to be face-centered cubic. And our stainless steels are typically some sort of a balance. The austenitic alloys are going to be mainly austenite, but most of the welding alloys we have will at least have a certain percentage of ferrite. So they're a mix of face-centered cubic and body-centered cubic. So not only are we trying to balance the chemical additions, but where are they placed sort of within this structure that we have of the atomic arrangement. So when we talk, I've had to briefly talk about solid solution strengthening. When we talk about A36, it relies on two major elements to be able to strengthen: the carbon and the manganese. And what you're doing with the manganese when you put manganese into the iron is you're replacing an iron atom with a manganese atom. And it kind of looks, the manganese is a little bit bigger in size. And so when you put this manganese atom inside of the iron, it kind of stretches it. It kind of stretches it and pushes it around, pushes around its nearest neighbors. And that change of putting a bigger atom into the iron matrix has a tendency of stiffening it. It has a tendency of locking up that matrix. And that allows us to increase the strength and change the ductility, changes the yield strength and the tensile strength. And the basis for that is called Hume-Rothery rules. So anytime that we're taking like a manganese alloy element or a molybdenum when we get to the T1s, or we're talking about the nickel, we're taking an iron atom, displacing it and putting in one of these big ones. Now, the other type of strengthening we have is interstitial strengthening. And carbon relative to iron is a really, really small atom. And so that carbon fits in between, like we see on the picture up there. It's a little atom that fits in between the iron atoms, and it does the same thing. It kind of stretches, but instead of replacing an iron atom, it's going in between. And I'm glad I noted, I have boron up there, and vanadium does the same sort of thing. So the boron atom that we saw that was really, really small, really, really small in amount. It was like 5 to 6 in the T1 alloy. That boron is really, really small, and it fits in between all of the other iron atoms, and it's really effective at locking it up. So when we talk about even an A36, think about that. As basic as we might think an A36 is, it's still relying on solid solution strengthening with the manganese and a carbon being interstitial. So there's a lot happening. And if I start just with the iron, so iron, not only does it have any iron, or steel rather, even the A36, you've got carbon, you've got manganese, and now you've got a phase change. So iron, when you heat up any steel-based, as you raise up on the plot is Fahrenheit. As the line goes up, the temperature increases, and then on the bottom axis or on the x-axis is time. So as steel cools down from 2,780 Fahrenheit, and when it's liquid, it changes into a solid, and that solid is actually a delta iron. But then it changes to gamma iron, and gamma iron is what we call austenite, and that's that face-centered cubic I brought up on the other, one of the first slides. It's the arrangement of the atoms. And as it cools down from gamma iron at 1415, at 1415, that austenite changes to ferrite. And really what that means is all of the atoms, it's called an allotropic phase transformation. All of the iron atoms have to shift from the face-centered cubic arrangement to a body-centered cubic arrangement. And so that helps to strengthen. You know, we often say that, what do we say? We say metal shrinks more than it expands, right? So as we weld, the metal expands up, and as it cools back down, it shrinks. And that really why it shrinks and it expands is it's going through the phase changes, the allotropic phase changes from ferrite to austenite. So that's a strengthening mechanism, and that's something that we deal with when we go in the heat affected zone. And if we shift and we cool it down too fast, as you guys, most of you guys know, if we go too fast from cooling from austenite down to ferrite, we're not giving the atoms enough time to sort of rearrange themselves. I normally use the analogy that if you walk into a large party room, or if we were at the welding show and you walk into a party room where you don't know a lot of people, you might walk in and you might find somebody you don't want to talk to for 2 hours. But if you have time to be able to move around, you're going to find the people that have the same sort of interests, and you have a good conversation going. It's kind of like if we can cool the steel down nice and slow from austenite down to ferrite, it's going to rearrange itself. And it's going to go from austenite to ferrite. If we quench it and we lock it in, it's going to go to martensite. And martensite is very hard. It is different arrangement. It's called body center tetragonal, and it might not be the happiest or the most equilibrium. That's where the party analogy comes into. If you only have 2 minutes to find somebody, you might not be the same group you would find if you had 30 minutes to find your group. So that's austenite to ferrite is a phase change. And if you don't give it time to transfer from austenite to ferrite, it'll go to austenite to martensite. Okay, so even with an A36, we've got chemical alloys or chemical additions we're adding in to strengthen the material, and we have cooling that can change. And this is the phase diagram. This is the iron carbon phase diagram. We're not going to get into it too much, although boy, that could be a whole talk on itself. But what we see here is we see temperature on the vertical axis, the y-axis, and we have amount of carbon, essentially. This is iron carbon or cementite on this axis. And we can see that as we add more carbon, what we're really looking at is how this line right here changes as it changes from austenite to ferrite. And so with more time, we can use this to be able to understand where your alloy is. And A36 is way down here. And then as we get into higher strength alloys with more carbon, it changes both the liquid temperature that it cools down, but then for our heat affected zone, it's changing the austenite plus ferrite region down in here. So everything we have is based on everything that we're doing. There's a lot of good books, and the welding handbooks give a lot of good information. Perlite is a mix. It's a diffusion limited. If we're able to slowly transform from austenite to ferrite, and our heat affected zone has time to be able to cool down nice and slowly, then we form this perlite, and it's a nice distribution of ferrite with laths of iron carbide or cementite that form in the middle. And so this is diffusion limited. It's based on the carbon atoms moving through the matrix. If we don't give the perlite enough time to form, this is the martensite. And so for a same alloy, we see that the perlite has these nice lath or sort of wavy texture to it. And the martensite's very angular and very acicular. It looks like needles. It looks like ice when it comes to freeze. And that's a diffusionless. We didn't give it enough time to move around. Okay, so some of the basics that I wanted to cover are the microstructure, and how we really use the phase diagrams, and the things that we do are the time temperature transformation diagrams. So this one here is done for a relatively high carbon steel. It's a 0.8 carbon steel, but it gives a good example. On the vertical axis, we've got temperature and ferrite, and we have time. So now we start talking about what we're really interested in is cooling rates. And cooling rates given and how long does it take to cool down. So when we look at a time temperature transformation diagram, this dotted line right here, everything above the dotted line is austenite. It's heated up enough red hot where whether it be weld metal or it be the heat affected zone, it's heated up and transformed. And now we see that you can superimpose a line, and normally I have one. I apologize, I don't have one. But if we cool this down extremely fast, if we quench it in less than 1 second, we would cool from austenite and we would hit this martensite temperature. And then you form martensite. And this is when we talk about welding with a 60-10 or arc strikes on this material. What we're really doing is we're heating that material up extremely quickly, letting it just quench. And so that's the same action as cooling right down very, very quickly. And that's why it's so important that most of our projects, we want to grind out those arc strikes and make sure that none of that has surface damage, because that martensite will cool down so fast and give a stress riser or give a susceptible microstructure. Same way, if we have a heat affected zone that we're letting cool down nice and slowly, what we're going to have is it's going to slow down and form this nice perlite, what we expect as it cools down to form first a ferrite, and then you have a primary ferrite, and then you have a perlitic matrix, and then it slows down nice and cool. I will say one more before I move on as we go through this. Some of the cautions, and the one thing I'll bring out with the A36 is certainly A36 can be damaged. But one of the most common things I've seen is they say, well, A36, we can't do much to hurt it. So, we'll either have a really high interpass temperature or we'll just keep it warm for a long time. And that can be equally damaging. A few years ago, I ran into a group that was doing some rollouts, submerged arc. They said, well, it's only A36. We don't have to worry. We just want to do one pass over the other. It was a large roll, maybe a 60-inch roll. But they were letting their heat input get pretty high, and they were letting their interpass temperature get up over 600 degrees Fahrenheit. And then they wondered why they couldn't keep their tensile strength up. And I looked at the 600 some interpass temperature, and what they were doing on the time temperature is they were just keeping that heat affected zone sort of nice and hot right up here for a really long time. And they were corseting. They were basically letting the grains grow so much that if you see this, it says coarse perlite. I think they were just ending up with just massive coarse grains, and they weren't able to pass their tensile test because it was keeping it warm for too hot. So equally damaging to keeping it, letting it quench too fast is keeping it warm for too long. I don't know if anybody's had experience. So some of the common steel mic, here's the one that I was thinking of that had the pads. If we cool things very quickly, like path number 1, again, this is temperature and time, you end up with martensite, which is over here in the lower right-hand corner. And this is all the same material. This is all the same steel. And you can take the same steel with the same elements in it. And if you do path number 2, they don't show path number 2. I probably stole the graphic from another place. But if you take path number 4, for example, path number 4 looks like this ferrite plus perlite in the upper left-hand corner is what it would look like. And this is what we'll probably try to achieve most of the time when we have an A36, a nice balance. I want to talk real fast. There's also continuous cooling diagrams, and this can get more into welding. If you really are dealing with a new alloy, it can talk about how the cooling cycle, now not only the rate of cooling, but how that cooling cycle is shifting some of these time temperature diagrams. So a fast weld cycle versus a slower weld cycle. And I think that there are a lot more of these in, I believe, the welding handbook. I think it's volume 1 they have it in. And so it's again the phase diagram, and where these would come into value is if you have a lot of experience with one of the T1 alloys and you're going to shift over to another high strength, you can compare your existing welding procedure to the new material that you need that is similar but slightly different. Normalized materials, I think we're going to move on. Normalized and quench and tempered. I think I brought it up. The as rolled material that A36 is, sometimes you can get an A36 modified. Sometimes you get some materials that are normalized. So the A36 is an as rolled. It comes off the rolling mill and lays out to cool. Some of the materials, particularly if you guys work with any of the 51670 materials, 537 class 1s, those are plate materials. A lot of those will be normalized. And so they take it back up into that austenitizing range. They let it austenitize, and then they let it slowly cool down. And that allows the atoms to move around and become a little bit more stable than we have in the as rolled condition. And that's different. The quenched and tempered, it also will take it up to the normalized, but then it cools it down really quickly. Then it brings it back up to a tempered, just a little bit below the austenite range. And that allows the coarse martensite to be a tempered martensite. So that the T1s now have, not only do they have all of the alloying elements in them, but they have this temper. And when we temper the material, now you have to be really cautious with the quenched and tempered materials, that when we go back through and do a post-weld heat treatment, for example, we want to make sure that we don't erase or allow the material to get too warm where it erases the effects of the temper. And this is why some of the 514 materials, most of the time, they would recommend as a general rule that there's no post-weld heat treat that goes on with the quenched and tempered 514. You'll see tempering or post-weld heat treatment happening with the chromoly steels. If anybody's doing the P91s, have to be quenched and tempered, or some of the 1 1/4 chromes, 2 1/4 chromes are post-weld heat treated afterwards. But the 514s have so many alloying elements, it's really tricky to go through and do a post-weld heat treatment. It's very, very tight as far as what can be done. So the basis of metallurgy, I hope we're doing okay. Is everybody hanging in there? Are we hitting the right topics so far? I can only see voice, so I hope you're hanging with me.
Yeah, from my point, we're doing good. As far as time goes, we're fine.
We'll wrap it up. We'll hit on the good topics here in the next section. Okay.
We may have to bring you back in May for a follow-up.
Maybe I'll do it in person. All right. So the reason why we want to talk, the reason why I had to lay some of the boundaries for the metallurgy is it really affects when we get into mechanical properties. I have tensile tests that are down here in the lower left-hand corner. The one on the absolute left shows a ductile tensile. So the things have nicely pulled together. You have ductility. The one on right next to it is a brittle fracture, something that it pulled, but it just pulled right apart. And everything that we build with metals, we like to have it yield or stretch before it breaks. We typically don't like things that are really, really strong, but just all of a sudden catastrophically break, because that's what they typically are, is catastrophic. There's too much energy. We like things that yield before they break. And that gets into some of the microstructure we see over here. And then this diagram in the upper left-hand corner is called a stress-strain diagram. When we pull a tensile, the stress is how much force it's taking to pull it, and then the strain is how much it deforms. And so we like to have these green type lines with most of our metal alloys that are nice and ductile. They have a lot of strength, but then as they start to yield, they start to stretch. Okay, and this is where we get into the heat affected zone regions. When I talk about welding, I have some really nice pictures here, but we talk about welding, I talk about it as a casting microstructure, because when we weld, it's sort of like we're putting metal into the mold. I had the pleasure of going to see Atlas Foundry up in Tacoma, Bradkin Atlas with Les, and they do some really impressive castings, and they're really massive. But everyone on the line, we're doing castings every time we're welding, because we're melting the metal up and pouring it in. And as we pour the metal in, it has it solidifies. And the picture here is a dendritic solidification. The weld metal, as we look, this is a nice picture that shows a multi-pass weld. I think that came out of the welding handbook. And it shows, looks like 4 passes maybe. But when we see these lines, and it shows up on my screen as sort of bluish gray, but we can see the lines, as you're familiar with when you look at your welds. What we're really looking at is the direction of those grains as they start solidifying. And our welds will solidify from the sidewalls, where the heat affected zone, and we can see the nice heat affected zone here delineated by sort of the halo in color. But the weld metal comes off that fusion line, and the direction as it comes off is called epitaxial growth. That means that the liquid starts to solidify, almost like when you put ice cubes in your freezer. You can sort of see the same directional growth, unless you have a really special freezer and make those really nice spherical ice cubes that they put in bourbon or whiskey. Those, you try to get it out so it's clear. But your weld will solidify coming inward. So we have a direct effect and a correlation between that weld metal and the heat input and the HAZ. All of these get stitched together to how it's going to work. And I had to put this in here on gas metal reactions, because I think that we can't just talk about the heat affected zone. If, for example, our weld metal is incredibly is much stronger, for example, than our heat affected zone, then it makes the heat affected zone the weak link. And if we make that heat affected zone the weak link, which is really narrow, that's typically where we get things like the underbead cracking, where the hydrogen will have a tendency to go to the fusion line and the heat affected zone. And that also can be a susceptible microstructure, like we talked about with the martensite. This is a really nice diagram that talks about how hydrogen can affect, and particularly our high strength welds, why when we're dealing with anything, but definitely when we get into the A514s with the carbon steels, you want to buy and make sure that you're using low hydrogen electrodes, and you're buying from a really good source for your weld metal, something that's going to have low hydrogen, it's going to have low impurities, because what happens is this diagram talks about the hydrogen actually has a tendency to go out into the fusion line, into the heat affected zone. And if we've ever experienced some of the hydrogen cracking, a lot of the times we can see that almost called underbead cracking, where it cracks right at the toe of the weld. It's a susceptible area. The hydrogen has a tendency of accumulating there. And then that's also where we typically have stress risers or increases of stress concentrations. The liquid metal reactions as well, as we start heating up and cooling down, we always talk about our joint design and making sure that, as that joint design narrows, we end up with a larger depth to width. And just like that shrinkage, and we know now that it's the allotropic phase transformations, if we have a really narrow depth to width, and that's the same with stainless steel, yes, you can end up with solidification cracking, particularly with the stainless steels, right, where it pulls itself apart, and that's why we like to have a wider angle. But also those liquid metal reactions can have a tendency, as it starts to shrink on the higher strength, you can put a lot more residual stresses at the toes of the welds. And so joint design can have a huge effect, not only obviously on the heat input, because if you have a wider joint, you can have a tendency to go to higher heat input. And that's why we need to step that heat input down and do split bead passes, or be able to distribute that heat out, so it's not as focused on the heat affected zone and has a tendency to shrink and pull together. Oh, that's a really nice picture. I forgot that I had this in here of the underbead cracking right here. So like I was talking about, is when we have some susceptible microstructures, this right here is a good indication of the heat affected zone, where most likely hydrogen also accumulated down in this region, and we had a susceptible microstructure, and we had residual stresses. So there's a lot of planning, not only on the guys that are welding, but really some of this needs to get feedback. And I know it's really hard, even in my company, sometimes to be able to get the feedback back up to the design engineers to try and work and make sure that we design out susceptible areas, try and minimize regions where we can increase the stress. We really want to lower the stress on the heat affected zone and the weld metal. Strengthening mechanisms, we talked a little bit about that. I want to focus on the carbon steels for now. When we heat that weld metal up, and the reason why the time temperature diagram is really important is, as we heat this weld metal up, that heat affected zone, we are seeing every possible different raise in temperature in that heat affected zone, and we're cooling down. When we're really close to the fusion line, we almost have that liquid. So we're raising the temperature way up, and now it's cooling down. But then as we step away, every point away from that heat affected zone is seeing a different maximum temperature. So it's almost like layers of an onion, where every layer of that heat affected zone is seeing a slightly different maximum temperature and then a slightly different cool off rate. So it's having a different time at temperature for each measure along that heat affected zone. It's another good weld metal out of cross section out of the welding handbook. This, I have to just show this. And like I was talking about layers of an onion, electrogas welding. I don't think that anybody has probably ever seen it, but electrogas welding is a lot of heat input. And it started, well, they use it to build like really huge oil tanks. It'll typically be in the Middle East these days. They still use it a little bit in the Gulf Coast when it's warm. I should say the electric gas welding, you use it where it's warm. You're not going to see it up in the Northwest. It's a little too cold. But, then last week was 13 degrees. So, I guess I don't know how the oil tanks made it, but electric gas welding, it could weld up to 1 inch thick steel, and they're putting a flux cord wire typically between two copper dams, and they'll weld 10 feet at a time between two copper dams. And as they weld up, it's basically just a liquid casting as it moves up, and the track moves with it, and it fills up the void. It uses, like 500 kilojoules an inch of heat input, which is massive amounts of heat input. So you have to use that with like an A36 type steel. You use it with like a 516, like unnormalized material. But the reason why I like it is the heat affected zone is really huge. And it's hard to tell on this, but this is a layout of a heat. This is the fusion line right here on the right-hand side of your screen. Where it's dark is where there's weld metal. And then the heat affected zone extends out. I mean, we're talking like, I don't know, a half of an inch is what this is. And then you can see as it slowly starts doing different heating. And now this is the base metal. You can see this banded. It looks like there's bands in it. That's the banded ferritic pearlitic microstructure. And you can see as the heat dissolves that away, as it got to higher and higher temperatures, then you see those bands get dissolved as the material was heated up so much and was at high temperature for so long that it caused all of the atoms to move around and completely change themselves. In fact, as we get over here, it's really hard to tell, but the whole grain structure and everything changes. And this was never liquid. We're just looking at a heat affected zone. What's nice about it is, for examples, is it's easy for me to show all of the different phases. But when we weld with gas tungsten arc welding, or if we weld with gas metal arc or stick welding, all of these same changes are occurring just in a really small package that's really hard to be able to distinguish out. But that still means that we have different areas of that heat affected zone that have reached different temperatures. And this is where slight changes in the amperage, the voltage, slight changes in even the weave procedure, if we differ from the welding procedure specification where it was tested, can have drastic differences on what our final weldment properties have out in the actual application. So this is a nice picture that talks about how, and this is why I brought the phase diagram up before. On this portion is the phase diagram that talks about the iron carbon. And now we have a temperature where we have the base material. This would be similar to an A36, a 0.30 carbon steel base metal, where this ties up to the maximum temperature of the heat affected zone that each distance away. So that, like that picture I showed before, if we're right there at the fusion line, it comes up almost to where it's liquid in this region. And as we move maybe a millimeter or 2 millimeter away, now the maximum temperature is still austenite, but it's not nearly as high. And so each one of these are seeing sort of these different waves as they're coming off. And we have this whole difference in microstructures that's occurring. I really wish, I know everybody probably wishes, I really wish we were in person because I'd love to ask questions, but here's where it comes from. If anybody has to do weld procedures, and everybody has different backgrounds, but I think API 1104 is pipeline. I think they have Sharpies that you have to do at Fusion Line +2, Fusion Line +5. Some of the DNV and the offshore specs have to do that as well. And if anybody's wondered why we've had to do so many of the fusion line Sharpies that occur right at the fusion line, 1 millimeter off, 3 millimeters off, 5 millimeters off, it's for the exact reason of what we're looking at here when we look at the heat affected zone. Some person had a failure probably at one point in time, and they figured out, well, it wasn't right at the fusion line or the HAZ. It was really just a little bit off. And so now they're asking for some of the welding procedures we have to do, that you have to do it at different distances along the heat affected zone, not just at the fusion line, which is sort of traditional. So because they know, I guess, and we'll see it later, what they know is we all know that at some point in time in the heat affected zone, there's a decrease in the mechanical properties. But now when you're trying to do it at different stages along that, they're trying to help you find where that decrease is, because there's some sort of softening. So when we talk about the heat affected zone, I think I'm going to get into the carbon steels. Obviously, the chemistry of the base metal and the heat treatment are going to be really important. A36 is sort of on one side on the bookend and 514s on the other side. But we have a lot of other alloys that we all deal with that are somewhere in between, that have a wide range of base metal and heat treatments, whether it's normalized material, whether it's quenched and tempered materials like a 537 class 2, I think is quenched and tempered. Testing my knowledge there just off the top of my head. But you get the chromoly steels, and then the 514s obviously are really critical. That welding heat input, whether you have big beads where you're having slow coolness, it typically, not always, but it typically will lower your toughness and lower your hardness. And then when you have small beads, there's like downhill stringers. You know, when I first started in the industry 27 years ago, and some of the structural steel in the tanks, it was really common for them to do vertical 70-18 up, and then they were doing 60-10 downhill stringers on the side, particularly for welders that weren't as good, because they would cover over their undercut. And I think that's gone away. But I had a few older gentlemen that had gone up to Canada, and 10 years ago, and they said, why aren't we still doing the 60-10 downhill wash? And of course, Canada, it was higher strength materials. And then with that lower temperature, when you do that 60-10, that really high heat and then fast cool down, it was giving them all martensite under. And that's just not the right way to be able to treat some of the higher strength carbon steels where you're getting that susceptible microstructure. The other thing that we need to talk about is preheat and thickness and how it affects cooling. I need to jump ahead a little bit, but the preheat and thickness, it's very common to preheat the materials in A36 or the 5/1670s. You really don't need to do much to preheat them. The reason why I bring up preheat is if you read the literature, a lot of the 514s and T1s were intended not to do preheat, because if you raise your preheat too high, then you're slowing your cooling rate down. And if we have too slow of a cooling rate with the martensitic, the quench tempered on the T1, we can actually cause a lot of coarsening. And so a lot of times people will think, well, I don't need to preheat a T1, but it all depends on the thickness. You know, some of these 514 weldments that are getting used more and more are crane bodies, a lot of offshore rigs where you're talking 1 or 2 inches. And thickness, there's a balance between preheat and thickness. If you have a really thick piece, then you're going to be pulling the heat out really fast from where you're welding, and it can have the effect of quenching that weld metal. It can actually quench, the thickness can act as a quench on that weld metal. So it's always important to think through what your cooling rates are, and maybe even use some thermocouples, or using at least some temp sticks, if nothing else. The temperature in the heat affected zone, this is the same sort of diagram that we had before, where we have temperature, and then we take a look at how it's quenching off. And it's not always just the heat input, like I tried to bring out, it's also your preheat and the inner pass temperature, and how hot the weldment is as far as how it affects how it's cooling off. So changing the cooling rate, and I guess I must have known I was going to talk about it, just jumped the gun. But not only is it the welding heat input, measuring your minimum and maximum, because not only is it maximum heat input, but particularly with the 514s, it can be the minimum heat input. Really teeny tiny TIG passes may not be the right approach to be able to take, because now you're getting multiple thermal cycles for the material. Sometimes it's better to have a moderate or even a higher heat input without obviously exceeding the welding procedure and what you can achieve with the material. But the heat input, having mins and maxes, it's also the preheat inner pass temperature. I put in there the 100 to 600 because it was from a different presentation. Typically 600 is only you'd see on the P91 type alloys, the 9% chrome 1 moly vanadium. But there's a balance. You know, having a preheat of around 200 does allow hydrogen to escape, and can improve your inner pass hydrogen devolution as it comes out. Some of these are pretty easy. Stress relieving is another way to deal with it. But what I really want to get down to is the A36 is relatively straightforward. I put in there the review of the CMTRs, and it's because I've seen some of the change. When we have a global supply of material now, it's pretty easy to make an A36 steel. You just have to have a yield strength above 36, and you have to have a tensile strength around 70. So I have seen material sourced globally that comes in even to distributors, and you look at the CMTR, and that A36 is not just the traditional chrome manganese material that we would anticipate. I've even seen some carbon manganese steels carry vanadium, which can really increase your hardenability. It's not something you're expecting. Some will have low levels of chromium and nickel, and it's kind of this plain vanilla material that some of the international steel mills will make, and then depending on how they roll it, can increase the strength, and you can turn it into a 572 grade 70, for example, if they do some controlled rolling. All I bring that out is always consider what your CMTRs are if you know what you're welding on, and you might be able to eliminate a surprise before it happens. I think the big thing with the 836 is just being consistent with that filler material selection, the quality of it, making sure it doesn't keep hot for too long. The 514 is really complicated. There's a lot of chemistry additions. The quench and tempered heat treatment really makes it that you can't do high levels of preheat. You really need to monitor that inner pass temperature. And there needs to be some really, you don't want to have too low heat input and too high. And I put in here the welding personnel. We talked about the welding electrodes. The welding electrodes need to be controlled and use good electrodes particularly, but talk about design. And the reason why is it's traditional for us to overmatch our welding filler material. And I have witnessed this occur before, is that by overmatching on already a material that's 120 KSI, I've run into some issues where folks try and grab 140 KSI weld material, and that is really challenging because now the overmatch, the weld material is already incredibly strong, stronger than the base material. The heat affected zone is going to have a little bit of softening occur because of that quench and tempered microstructure, typically, and then they'll end up with cracking or the fabrication sequence. There was one example I had. They were doing the bottom of a crane. It was like, I can't remember the manufacturer they were using it for, but it was sort of like a large Manitowoc type crane body where it had a pretty wide base on the crane. And then they were doing the vertical walls. And as they were welding around, they were welding out their fillet welds, but they weren't doing any offsetting where they were welding one side, welding the other side around the base. And as they got to the last 6 feet of that base that was all welded up, they had so much residual stress. They had clamps holding the thing down to form. And questions always come in kind of funny. They say, why is it cracking? We think something's wrong with the weld metal. And, you know, as we went through, it wasn't the weld metal. It's because they had so much stress in that body and it had no place to move. And they were also using an overmatched welding consumable that last material just had nowhere, and it would just pull itself apart. It would crack. It would typically crack right at the bead of the weld. So trying to work. ArcelorMittal has a great website. They own the rights to the T1. And the two documents that I like is they have one that's called How to Weld T1. And the other one that they have is Guidelines for Fabricating and Processing Plate Steel. And the reason why I like the How to Weld T1 is that it's written into some of the other literature, like the 514, you don't have to do a preheat on it. But in the How to Weld T1, they really go into a lot of detail and says, no, if you have really thick weldments, you really need to be considering your welding consumables. Maybe you need to match or even undermatch depending on the application and the design. And then they give some better guides with controlling the heat input and controlling how the microstructure is changing with heat. Oh, do you want me to just hit a little bit of stainless and aluminum? Do you want me to speed it up, boys?
Well, we have some questions so far. Let's take the questions we have. And then maybe what we can do, we'll get the group's input real quick, is we can schedule a follow-up in May and come back and do the stainless and aluminum, or do we want to push through for tonight?
I'm really sorry I went over. I should have spoken quicker.
No, you're fine. Okay, so I know we have some questions in the chat. So Anna, you can go ahead and unmute yourself.
Okay. Can everybody hear me okay?
Yes, I can.
That's right. Everybody's muted. Okay, the first question that we had was, there's two questions that relate to underwater welding. And the first was, how is metallurgy changed during underwater welding?
Okay, that's a good one. I figured out how to get the chat. I'm sorry, a little bit late. I should have figured that one out before.
Oh, that's okay. We were keeping track.
Underwater welding is a total different animal. In fact, the electrodes are totally different. The electrodes will have a huge amount of flux on the outside. If anybody knows more about underwater welding, please raise your hand, because I've never done it personally. I work with a guy that did it, but they'll have a lot more flux around it. When they do underwater welding, they're typically not going for long-term quality on the ships. They're going for fixing a pinch, something that's really bad that's happened. If a ship needs to have some major fixing on it, they'll take it out of dry dock for the exact reasons of trying to keep the metallurgy good and proper. I attended an AWS seminar from somebody that did underwater welding, owned a company. They do a lot of that work. They'll do some in California, but a lot of the work is done in Curacao, and it's done in Aruba, down in the Caribbean. And they'll take cruise ships, they'll take ships that are passing oil through the Panama Canal, and it's really only done to do a stopgap issue, just to get them to a port where they can take it into dry dock and do the fixing. But underwater welding has typically stick electrodes, and they'll have a lot of flux burden around it, so that it cavitates the water away and then creates a atmosphere, a clean atmosphere, as clean as it can possibly get on the inside. Does that help?
I think so. So does the same apply for, like, I've seen some videos on YouTube of like underwater pipe welding? Does the same apply?
Probably. I haven't looked at the videos. There's other ways that they can do it as well. So sometimes they'll put an atmosphere and they'll pump the water out if you need a higher quality other than stick welding, and they'll do sort of like a glove box type welding as well. I don't know how they're doing the piping. I'd have to watch it, but yeah.
Okay. It looks like the person that asked that question threw in afterthought. It says, we mainly do temporary anodes on docks and structures. It's difficult, but I've always been curious about the metallurgy. So does that extra big flux help protect the weld environment?
It does.
Like what you mean? Okay.
That's kind of like even with the stick welds. When we weld with stick weld, you're burning off, and it's kind of, I used like Pigpen and Charlie Brown. You're kind of creating this inert cloud around it because we're not using argon gas to be able to displace it, or CO2 and argon in flux core, right?
Okay, so like
places.
The water doesn't necessarily affect it doesn't necessarily quench the weld or anything after.
No, I mean a little bit, but most of the materials that they're doing underwater are not as sensitive to that. So yeah.
Okay. And then the next question is, with rapid quenching underwater, is there a risk of the martensitic crystal structure forming?
There would be, yeah. Anytime that it's in contact, it can have a tendency to cool it down and quench it. Yes.
Okay.
And one of the questions I saw was, people want to know if they can have a copy of your presentation.
Sure.
PDF. And I figured that was the answer, but I wanted to check with you. I mean, it is your IP, so.
I'll do a PDF. You can see I don't put a lot of words in the thing, so it's hard for anybody to really read my mind.
I think mostly they wanted the charts that were presented.
Yeah, absolutely.
And then if anybody else has a question, just go ahead and type in the chat your question. And Anna can ask it, or if you want, I can unmute you and you can ask your question directly.
I do have one more question, boys.
Okay, go ahead.
Go ahead and ask that. It's a really good one. I'm looking forward to the answer, Ben. Most materials have been recycled and remelted. How effective are the foundries in controlling alloy content? And how much of a concern is unintended microalloying and metallurgical effect?
That is a really good. That's a really good question. So I'm always sensitive with time, but that's why some of the 836 materials we're seeing are having different types of alloying elements that we wouldn't anticipate. And the reason why I bring it up is, for people that have been doing this for a long time, I haven't been doing it for a long time, but I've been doing it for about 20 years. You assume that some materials have, like I say, 836 has carbon and manganese. Same thing with some of the 516, 60s, and 70s. I figure, well, it's going to have carbon, it's going to have manganese, and then you have some issue that shows up on a WPS, and you go, why? Well, look at that. It's got some vanadium, it's got some niobium, it's got some of these other, and this is what's starting to happen into the recycling market is as they're recycling the materials, depending on where you get your material from. I'm trying to say it nicely. So we have a global supply of materials. If you get your materials from a good, reputable steel mill, it's going to be probably pretty clean. But there's a lot of sort of smaller mills or mills that it's getting melted in another country, and that country then sends it to another country to roll it. And those you really need to be careful with the CMTR. And so it's not just, give me a second, it's not just the carbon steel alloys that are starting to see some issues. I'm not as adept, but I saw a question in there about titanium. Titanium is starting to see some issues where you're getting other elements creeping in that can be detrimental. So yes, that's what's really important to look at your CMTR. Even when you think you know what the material is, take a look at what you're dealing with and making sure that it's the same quality. A thing that I run into, guys, with this is when you need to do a PQR really fast and it may not be the same, a lot of material you're going to use for fabrication. And so you go to a material stockist or somebody that has it on stock. They may have material that's not the same quality that you're going to buy for your project. And it can give you some real heartache when you go to do your procedure qualifications and your Sharpies and your tensils. Does that help?
Yeah, quick question for you, Ben. Looks like a lot of the people are asking that we split out the stainless and aluminum for a follow-up. Are you available for a follow-up in May?
Yeah.
All right, there you go. Everybody, we'll have Ben back in May for a follow-up presentation on the stainless and aluminum. And when I spoke to Ben to set this up, I knew this was going to be a big chunk to bite off because he has a lot of wonderful information. So,
I'm really sorry I went over. I knew I had too many slides, but I can come back and reinforce. I guess what I was trying to get after is when we talk about the heat input, there's just so much that goes into that weldment, and helping to understand sort of the crystal structure and the way the materials gets made, I think helps us understand why it's so critical and why some of these welding procedures are so tight. Because even in my company, we'll have welding procedures, and if you get out in the field, the guy says, "Well, man, it welds so much nicer if I just pop up 2 more volts and a little bit more wire. It welds so much nicer. Look at it; it looks great." I say, "I know it looks great, but you have to look at what the weld metal is, and if we could weld it with higher heat, we would, but we just can't pass the test with the higher heat input."
All right, so safe person's logged in as safety. You had a question. I went ahead and gave you permission to unmute. So if you want to, go ahead and unmute and ask your question. Okay, I'll ask you for him. Then it says, does welding underwater add hydrogen to the weld from atomizing the water?
No. So, well, I don't know if anybody does self-shielded electrodes. I don't think it's any worse, and I'd have to look up the numbers. It's probably no worse than like an H16 maybe, because the coating on that is so thick that what you're trying to do is you're trying to boil and remove all of that the H2O that's around it. So you're trying to basically create a gas pocket. So I don't think that you're going to get too much more hydrogen around from the water than what you normally would.
Okay.
It's, what it's probably like. you have a lot of different ages, but maybe we'll see. Remember like jet rod back in the day, like 7024 or 7028, and it had like a 1/4 inch, and you could just kind of hold it, and you could look away, and you could just weld because it would just liquid and go out. That's kind of like the rods, I guess I would say are.
Okay, and then we have a question from Dennis McJunkin. He wants to know, is there any references to calculating cool down rates?
There are. Guys, he'll have to email me on that one. There's yes. Yeah, man, that's a whole nother one. I should have probably got into that. There's what they call the T8 to 5, which is 800 to 500 degrees centigrade. And it has to do with how much time it spends at that temperature. And then there are some calculations. The reason why I often don't bring them up is they can get a little wonkish. And sometimes they're hard to count. You have to be able to plug some data in. But I'll tell you what, I could look that up, and then if you want to email me, my email should be there, or I can put it in the text or something. Yeah, I can get those to you. Yes, if you have the same design and you're doing fabrication and you have the same design over and over again, it can be really valuable where you put some thermocouples, and then you can do some calculations based on the heat input.
And then we have a question that says, with technology processing main members, is the etching of numbers on beams and columns with a plasma robotic arm causing any issues with the metrology?
So I saw that question. I don't think so. That's a great discussion if the person can help me talk that one through. So we have a lot of etching on, we do mainly pipes. We obviously do structure. When we're talking metrology, we're doing some LiDAR scans and some small laser interferometry for metrology, where we're doing fit up. I don't know if that's the same type of metrology we're talking about. Do you know, Boyce?
I don't know. I'm gonna, I gave that person permission to unmute themselves. So if they want to unmute.
I would say in general, if it's metrology, we're talking like measuring, no, typically the etching is too shallow. If they're talking about metallurgy, let's take with metrology, if you're doing measuring and LiDAR, no, it's too shallow. If we're talking about metallurgy, there are rules actually to a lot of the etching. So that's a really good one. Because when there's marking, well, kind of the same with anything we do marking. Use the same, I'm going to use the analogy of when we do stencils, right? When we do stencils, depending on the material, you have to use the low stress stencils that are more shallow so they don't do a notch. Same thing with some of the etching. Not all materials can be etched, but the etching is not as much of a concern on most of the structural steels we have, like the A36s. It'd be really hard. The carbon is low enough that it'd be really hard to get, give me a second, to get the martensite to form, even with some of the 57250s. But typically, if there's a material that is sensitive, they won't let you do it. And I see some of the abridged does not let you etch. That's probably true. With the materials that you get into bridging, you get into some of the higher strength. You're probably getting into, and somebody's here is online probably going to help me, maybe an A709, like some of the weathering type steels, getting into 80, 90 KSI. It can be an issue. And so there are limits. And I think that we have limits on what we can do with measuring, marking. I'm thinking about power type infrastructure when you get into the P91s and so on that are really sensitive to that. So yeah, there's probably limits.
The next question is from Dr. Khalid Khan. He says, can we say that heat input should be kept to a minimum in all cases, or is there a magic optimum heat input that we should shoot for?
That is really good. I wish there was a perfect answer. It really depends on the alloy. Some you can have too low of heat inputs, so there needs to be mins and maxes. You know, I don't know. You know, a lot of the things that we do, like when we do submerged arc welding, I don't do rollout, so I do submerged arc welding in the horizontal, and we do a lot of cryogenic steels, do a lot of carbon steels. We'll do some high strength. You know, our heat input is generally like 35 to 45, 50. Even when we're doing flux core welding, when we do flux core where you can do higher heat input going vertical up, we typically have a maximum range. Even on easy alloys, we like to have a maximum of 75 or something like that. You know, there was a time where people would do really wide weaves and carry a lot of metal. Somebody here that does structural welding, I wish we were in person, but used to do a lot of really wide weaves, 75 kilojoules an inch. It's kind of what I say, 75 kilojoules per inch. But there used to be a time, I remember seeing PQRs from the 80s, and people would carry with a flux core gun. You guys remember? I need somebody that's older than me, when they would make the huge flux core electrodes, or even you could get a 1/4 inch 6010 back in the day. Boyce, you remember this? You're the only one online.
I've seen pipe welding with 1/4 inch 7018 at over 300 amps. You
know? So a lot of that went the way of the dodo bird for a couple of reasons. One was the materials now have more higher strength, and it's harder to be able to get the mechanical properties. But the other one that's a natural limit, Boyce, in my opinion, is the quality, because when you're carrying that much metal, it's so easy to trap things. And now our X-ray and our ultrasonic technology is so much better than it was 30 years ago. I don't think you can get away with that. That's my general opinion.
A lot of what we see in the structural side is in D11. There's no heat input limits. So in theory, you use flux core, you could just put in those big, 4-lane highway type weaves, and be pushing 80, 90, maybe even 100 kilojoules easily.
Yeah.
Now, when we get into D18, and there's a lot of D18 in this area because
that's tough.
We are in the ring of fire. We do have seismic, and there a lot of contracts are pushing D18 more. Then you have to have the manufacturers certify a low and high heat put.
Yep.
So, like we take a Select Arc, since they're in the room here, and they have a Select Arc 720, which is a 71 T1 wire. Your heat input range will be somewhere around 30, depending on your diameter. You'll have 30 to say 70.
Yep.
I personally write my WPSs and train my welders that the optimum I want to see you doing with a flux core with a 71 series wire on a 836, 8572 grade 50 is about 45 kilojoules in a vertical and about 50 in a flat.
Yeah.
I don't really want to see you in the 30 range because yes, you'll make it, but you're not optimized at that point.
Correct.
You're not producing your maximum efficiency. You
Correct.
can do more, but I also don't want to see you in that 70 to 80 range because just because the manufacturer's tested that doesn't mean that's always the best thing to do because like you said, the 836 is such a wide fat cow with what can be in there. You don't know if it's a 5% fat or a 45% fat piece of meat that you got.
Yeah, I really appreciate that. So to the answer to the question, I wish there was an easy answer. I think it really changes. I like the ranges that you gave because those are kind of just my off. Everybody has to do their own, but that's a good range. Here's how I look at it, Boyce, and maybe you can agree or disagree. I look at it like gears in a car, okay? And I've never driven a Ferrari, but I know you can rent them in Miami. You saw Justin Bieber some years ago get in an accident or whatever. But, if you go and rent a Ferrari, they don't give you access to every gear in the Ferrari, right? So when you look at heat input, just because you can, like you said, just because you can go up to 75 and it's the maximum, it's probably not the best idea to be redlining it, right? Going down the street.
Absolutely.
And I like somebody wrote still doing the wide weaves till the cows come home. I don't see it very often. I'll still see it sometimes in the Gulf Coast with some of the fabricators, and you see somebody like doing a weave that's like 1.5 inches wide, and you kind of stop and you go, wow, I haven't seen that. That's like old school. And yes, somebody wrote, I don't want to see Sharpies because I don't know how they get Sharpies. They probably put it in backwards. They just forget to put the notch in. That's how they pass.
That's the thing with the D11 pre-qualified is you don't need the Sharpies, but in the D18, you do. You have to have the Sharpies low and high. Now you get into the bridge, you go even more restrictive because you have to run the PQR and prove it, and then you get a window, depending on how you do it, you can do your heat input minus 40%, so you get a 60 to 100. So if you qualified at a 50 kilojoules, you could get 50 down to 60% of 50, which is 30 kilojoules.
Right.
Qualify high-low methods, but you basically have to prove that whatever kilojoules you're going to use are actually working, So it helps stop those, like I say, the 4-lane highways. It really annoys me when I see the 4-lane highways.
In my past lives, I've seen it where, the switching people over from doing the wide weaves, there was a real struggle because generational, that's how it was done, doing really, really wide weaves. And then as the Sharpie impact numbers dropped, or particularly when where I was before, they started doing a lot of work up in Canada, up in the oil sands where the Sharpie impact temperature was minus 40. You couldn't get away with doing that. And as I switched them over, there was a lot of resistance, but what they realized is their quality actually improved by going to split beads. It really doesn't take that much longer. You do another pass, but it's easier to inspect it. You have better built-in quality. And then of course, you pass your PQR and you have good built-in quality the first time, right? Which is the real reason. But what they found is that there's other tangible benefits by immediate benefits to the quality aspect.
So Arthur just posted something in the chat that I know we've presented on this a couple of years ago. I did some serious presentations on WPSs and stuff. Is, believe it or not, AWS, if you look in B5.1, it says that your WPSs should be, now that's not a shall, it's a should be written by a senior CWI, or it can be written by a welding engineer, but when we're 5.1 is talking specifically about welding inspectors, okay?
Yeah.
And it should be written by seniors because they've had time to learn what's going on with the processes and stuff like that. When you get into the world of pre-qualified, just having something say, okay, well, the manufacturer says I can weld at 21 to 30 volts and I can weld at 140 to 300 amps. It doesn't mean that every single number in the middle there will give you it means it'll give you a weld. It doesn't necessarily mean it'll give you a weld that meets the design intent.
Right.
And that's the reason you need to really understand your specifications. What is the application? What is the specification? And unfortunately, a lot of that information doesn't flow down to the welder in the fab shop. It stops. Sometimes it doesn't get to the project manager. It gets to the general, it goes down to the fabricator. They get busy, they sub it out to someone else, and they say, here, just build this. And they don't tell them all the design intent, all the specs and stuff, and all those little things in there as to why. So like you said, it's really important for the welders and the fabricators to ask questions up the chain of, this doesn't look right, this doesn't feel right, what's going on here? Why is, this?
Yeah, it's sometimes that's impossible. I know where we all live, when we all live where we are, sometimes we're subcontractors, we're working for other people, people are looking at what we have, and we don't have the ability to talk about it. But yeah, it is, if we can get involved early on, and I'm going to answer the question there really fast that came out, it's a good one, but I've witnessed a lot where people have, a shop has always used A36, and then somebody, the owner of the small company says, hey, you know what, guys? We can make this a lot lighter if we go from a 70 KSI material to 120 KSI material, right? I've seen that multiple times. And they don't consider that, hey, wow, fabrication is totally different, right? It's not just, you can't just switch over. You've got to talk about weld sequencing and everything else. So if you are past I should say this, if you are past a bad deal and you've got to figure it out and you're on the weld shop, I would like to tell the folks, there are people you can ask questions. And what is nice about the welding industry is I think that if you pick up the phone to anybody, even if a competitor called me up and they had an issue and they had a real concern, I think that we would dig out and help them. But there's a lot of resources that are free that you should never hesitate to pick up the phone and ask. One is the people that make your material. Just if you have a CMTR, pick it up. They have a technical department and they have people that know how to weld. They invest money in that. And then the people that make the welding electrodes. And if you don't get anywhere with your local rep, you can call up other numbers. You can call me. I'll get you in touch with somebody if it's that bad. But the welding companies all have folks that deal with the design and the qualification. They know how to use the product. And it is essentially, they're there to help you be successful. Seriously.
And I don't know if you saw those other two questions in the bottom of the chat. I'd like to see if we could get those answered before we have to.
If calculated heat input exceeded during production welding, what remedial action needs to be done? Is that the first one?
Yes.
So that one there is a tricky one. Somebody else can help me with that. Typically, you have to do a non-conformance report. But when we've run into that before, if you're outside of the heat input, you can, and Boyce, you can help me, but typically I've seen, depending on the code you're working with, if you can weld up a test plate, you can do a procedure qualification with the higher heat input, then you can qualify it. Boyce?
My quick short answer is you were correct, right? The NCR, contact the engineer of record. Okay, that's the answer I want everybody to learn. Get a hold of the engineer of record, because it's ultimately that engineer's stamp that says that that building is not going to fall down if you did it the way he wanted it. So if you screw it up, he needs to know, or she needs to know, so that they can do the calculations and figure out. And they may come back and say it's not a problem. Then they come back and say what Ben says is weld up a sample of that, and if we can prove mechanicals, it's acceptable. Or they may tell you that they want you to do a heat treating of some sort, or a tempering or a quenching of it to restore some of the properties. But the big thing is you must notify the engineer of record so that they make the ultimate decision. It is not your decision on how to fix it at that point. If you violated the specification, you need to let them know, let them decide what they want done. Etching in D18, I don't know of any document that says that you cannot etch in D18. I know bridge is restricted. Bridge says it has to be low stress. So. Go ahead, Arthur. Go ahead, Anna.
Ben, I wondered if you wouldn't mind, if you had an email that you wouldn't mind sharing in the chat for people that could send you a few more questions. And then we're all really looking forward to a follow-up meeting with you, a follow-up lecture with you in the next coming months. I do have one person that is specifically requesting if you wouldn't mind sharing your PowerPoint presentation. I don't know if that's possible with your company regulations or whatnot, but
I'll do it. I'll put it in a PDF format, and Boyce, I'll send it to you. Is that okay? And you can distribute.
Absolutely. Send it to me and we'll get it distributed.
Awesome. Anybody that wants it, if you want to chat me your email address and I'll write it down here. I really appreciate that, Ben. And we look forward to seeing you again. This has been a wonderful meeting.
I appreciate that. And yes, there's a good comment. Arthur is very correct. I should say anything I'm doing and giving comments or my commentary, they're not code advice. And Boyce, you did a good job in talking about the engineer and record. It's challenging because there's so many different codes. So everything I said was just colloquial. No. It was very good. That's why I'm always kind of hesitant. The answer I gave you was the back of the envelope we're having a beer at a bar answer.
No, and I agree. And that is the thing is that, like you said, you talked about Sharpies with API 1104. we do a lot of D11, D12, D18, D15 in this area. There's some 1104, there's ASME B31.3, ASME B31.1, ASME Section 8, ASME 1. So there's hundreds of codes out there. And then there's projects that don't have codes, but they have specifications. And then there's projects that don't have either one.
Correct.
But so there is no quick, fast, pat answer of every situation you can do this.
That's why it's hard. But I hate giving the answer. I hate giving the engineer's answer of, well, it depends. But it does. It depends.
If I like Arthur's suggestion, Ben, if you're okay with that, is once you send the PDF to me, we'll just MailChimp it out to everybody that in the section.
Sure thing.
MailChimp's our mass marketing email system that we use.
No, I appreciate you guys having me, and who knows, maybe in May it'll be safe to travel. I've got no problem in making a trip up there, and I can probably tailor a little bit better to the needs and understand the group a little bit better. And guys, I gotta be honest, it's really hard doing these things on Zoom, I think, because I'm kind of the type of speaker I like to see people's face, and it helps to understand what you guys are building and fabricating and the codes you're dealing with. So appreciate the opportunity.
But yeah, if you can make it out in May and the state will let us, we're definitely open for that.
Yeah, I just signed my folks up for the second dose of the vaccine in Tacoma. That was, I think it was easier to place bets on chicken fights in Louisiana 20 years ago than it was to get them a vaccine appointment. Madness.
Absolutely agree with what Arthur just said there. That's the reason when people ask me questions, and I'm actually a consultant for a living. That's what I do is get paid to tell people what to do to comply with the code and specifications. I like very specific questions. It's like, can I do this? What are you doing with it? What code are you working to? What time of day is it? Are you doing it with your right hand or your left hand? And I'm gonna give you a very specific answer for a very specific situation. Because I hate doing those blanket statements where then all of a sudden they say, well, Boyce said I could do this. Well, when Boyce saw you doing that, you were welding flux core on 836 and you were not welding, GTAW on stainless. So there's a world of difference.
Yeah, that's complicated.
Do we have any more questions on the presentation? If not, we'll take general questions about the section if anybody's got one.
I do have a question for everyone that put their email in. If you are not already added to the the Portland AWS board email list, is there anybody that does not want to be added? If you do not want to be added to the emailing list for future AWS meetings, let me know. Otherwise, we'll just add your name to the list and you'll get notifications for future meetings, as well as a PDF format of Ben's PowerPoint presentation. So it looks like Gloria is wondering if a rapid cooling of water quenching would be enough to affect a bend test.
What material? How was it welded? Water quenched 836 probably will pass bends. Water quenched 572 grade 60, you'll snap it every time. Well, you shouldn't be water cooling any weldment.
Yeah.
But 836 water cooled in the right thicknesses would probably still bend. I mean, 836 normally is a fairly easy material, but You can mess it up. Oh, see, somebody went ahead and muted Ben. There you go, Ben.
I muted myself because I thought I was done. Then I couldn't unmute myself. Yeah, boys, you're right. You know, I guess when in doubt, don't water quench. I know that's can be common in some test shops, right? If they're doing bending as a qualification, they quench it after they cut it out. I mean, when in doubt, don't do it, right? That would be a mistake.
Here's my theory on that as a, because we do welding tests and qualify welders. Let's just say, for this presentation, I'll pick on Ben. Let's say Ben welds it up 836, and I water quench it so I can cool it off and handle it, start cutting and processing. If for any reason that Ben failed, in today's litigious society, Ben can come back and say, the only reason it failed is because you water quenched it, you screwed up my weld test and cost me a job. Why would I want to do that? Why would I want to put myself in that boat? Let it cool down. It's going to take a couple hours. Let it cool. There's no reason to rush it.
Yeah, I mean, at least when we do procedure qualifications in our test lab that we have, you're right, Boyce. We don't do the quenching down, I guess, for the same reason you just brought up. Yeah, but we normally don't do 836 either. We're normally doing like P91 or some weird thing.
Yeah, I don't like taking chances with people's tests, so we're just going to let it cool naturally. We're not going to use a fan or anything, and then when it's cool, we'll process it, give you the greatest chance of success, greatest chance of passing that test. Brian, you're unmuted. You can unmute yourself now.
Yeah, I was just going to say that we do that class quench. We have quench tanks and everything. We've done extensive testing on it, and you're correct. We do it in class just because class time is vitally important. But my class also knows that we do not do that when we're taking any type of 1-inch unlimited tests or anything like that.
Uh-oh. So, and then I see a lot of chat back and forth about certifications and qualifications in the zinc. And that's another thing that completely on code. In structural world, you qualify process, but you also qualify, like in D11, you qualify with carbon steel, you're qualified to weld carbon steels. But when you go to D16, you got to qualify again. You go to ASME 9, you can actually take an ASME 9 P1 sample, weld it up with a 309L, and be qualified to weld all carbon steels and stainless steels. Well, not all, most carbon steels and stainless steels with just one test. So depends on what code you're actually qualifying to. Arthur wants to be unmuted. All right, Arthur, you can unmute yourself now.
In regards to the quenching thing, I mean, even especially as students, I mean, I would highly recommend that you are welding just like you're going to weld out in the field. When something is hot, you're not going to grab a hose and spray it down. A lot of time, the parts that you're making are much larger than the quench tank that it's going into. So, especially if you're testing, why would you work against yourself first and foremost? But I would get used to understanding how you let something cool. I would get a box of crayons, heat crayons, not Crayolas, and understand what it means to watch that go down, and that'll help teach you about heat input. They're really cheap and they're easy to throw into your bag.
Yeah, we go through that.
Any more questions? All right. While you guys are thinking on that for a second, I want to go ahead and do the announcements for the section. Obviously, we're going to have a meeting in May. We're going to have Ben back. We don't know if we're going to have a meeting yet for March and April. We'll figure that out this weekend because that's when we have the board meeting. We have our board meeting this Saturday at 9 a.m. If anybody would like to attend that, it's going to be in Zoom. You can. The only thing I ask is that we'll do the same thing we do here. We'll have the people who are watching muted while we have discussions. And if you have a question, you can ask in chat and stuff, just because we don't want the meeting to go on for 4 or 5 hours. But you're definitely willing to come. And if you have input, you're more than willing to listen to your input and have you provide it. So if you want to attend the meeting, it is this Saturday, 9 a.m. Send an email to section@portlandawf.org. I'll type it out for you, and we will forward you the invite. We're also looking for volunteers to help out with the section. So if you want to volunteer, please go ahead and send an email, and we can always find something for volunteers to help us with. And then, so we're working on meetings. We will try to have a meeting March and April, but we don't know what they will be yet. And then June, we will have, the end of June, we're going to have Oaks Park, provided that the state lets us and everything's opening back up by then. And then in end of August will be the shotgun shoot again down in probably the same place, Mid-Valley Clays. We seemed to do really well with that last year. So, and those events are open to everybody. Portland, Seattle, Tacoma, Spokane, Inland Empire. Finn, if you want to come up for any of those events, you're more than